So, good morning. I would like to welcome you on the first session on this morning in Hall 2. Today our topic is chemical reaction engineering and reactor design, and we will focus on novel experimental approaches, modeling, scale-up, and optimization. So there are a lot of interesting talks in front of us. It's actually my big pleasure and it's an honor to chair this session, and my name is Tilman Schildhauer. And now I will introduce the first speaker of today. It's Professor Mikhail Sinev from the Semenov Institute of Chemical Physics of the Russian Academy of Science in Moscow. And he will give us a presentation on parametric sensitivity and design of reactors for chemical processes in water fluids. Professor Sinev, the floor is yours. Please.
Thank you very much, Mr. Chairman. And I say just hello to everybody because we are in different time zones. Some people have mornings, evenings, or afternoons. So just hello to everybody, and thank you for joining us. So what I should do first, probably share the screen. Yes. Then can you see my screen?
Yes, we can see it. If you now go in presentation mode, it should work.
Okay. Okay. Now, the topic of my today's presentation is processes which we proceed in water fluids at high temperatures. And I will talk about the parametric sensitivity and reactor design for this kind of processes. And why water? It is well known that water is the most abundant and widespread substance on the Earth. And probably it's one of the most mysterious and even enigmatic substances as well at the same time. So it's very common, but not ordinary, seemingly simple, but too complex. And I will try to show you it in a few minutes. What is my personal motivation for choosing this topic today is that I want more to share difficulties which we face when we are doing experiments in water fluids, rather than achievements that we've got by now. And I will do it as an experimentalist who is running studies on both commercial and homemade equipment, and as a secretary executive of the journal which publishes papers devoted to the research in supercritical and subcritical fluids. And a couple of words about water. We all know that this is a universal solvent for many inorganic and organic substances, and a well-known medium for many types of reactions. This is the greenest possible solvent and reactant in the world. It's fully miscible with nearly all gases and vapors at temperatures about its critical point. And it has a very high sensitivity of physical and physicochemical properties to state parameters in the vicinity of the critical point. And I will talk a little bit more about this issue. If we look at the phase diagram of water, we will see only two areas where, water properties can be described rather simply. It's in the first area of very low densities. It's an area where properties of water vapor are close to the properties of the ideal gas. And on the opposite side of the density axis, where water is nearly an ideal incompressible liquid, but we are more interested in the area around the critical point where the properties of water cannot be described in such a simple way. And if even very small changing of parameters would lead to very dramatic changes of the properties of water, so we can talk about very different areas where water possesses different properties and different behavior when we vary physical parameters in a very narrow range. So, and everything is due to an interplay between molecular forces and thermal motions of water molecules in the fluid. And here on this slide, I demonstrate you just very briefly how different properties of water, water fluids, which can be important for the processes which we are studying in this media, vary with density at temperature about just 5 degrees above the critical point. Here we have relative density, compressibility, transfer parameters like viscosity and thermal conductivity, heat capacity, speed of sound, internal energy, and entropy, and all those important properties change in a very different and complex way when we vary water density without no changing of temperature. And if temperature and density change simultaneously, we have much more complex behavior. And talking about the types of reactions which we can study and run in water as a medium and with water as a reactant are very, very superficial and very brief overview. We can talk about ionic reactions, like, for instance, hydrolysis of different types, redox reactions like corrosion and so-called supercritical water oxidation, etc., and many other types of reactions, including catalytic ones. And today I will more focus on ionic type of reactions in water and with water. And the most important properties of water when we talk about ionic reactions are, of course, its dielectric constant and ionic product. Both those characteristics of water change very regularly when we talk about the dependence on temperature and density. For instance, the electric constant smoothly decreases when we increase temperature at constant density and increases when we increase density at constant temperature. The ionic product of water, and so concentrations of protons and hydroxy groups in the fluid also changes very regularly when we change temperature and pressure. But if we are running the process at constant pressure, not at constant density, these parameters change in a very strange way, especially in the vicinity of the critical point, and we will never understand the nature of such a behavior if we do not take into account how density changes at constant pressure with the temperature. In this area, we have a dramatic change of density, as we saw on the previous slide. Density is one of the major parameters which control the properties of water fluids. And we can conclude here that isobaric dependencies do not reflect or sometimes even distort the physical picture of the process and phenomena in fluids in the vicinity of the critical point. At this point, I would like to say a few words about the reactors for such processes. Here I list very briefly and with no details some requirements to this kind of reactors. Of course, strength and tightness, materials, safety issues, but I will speak a little bit more about the measurements and control. And since we are talking about the parametric sensitivity, we have to talk about the parameters which control the properties and reactivity of water fluids and different substances in water fluids. And in different types of reactors, we have different possibilities of measurement and control of those parameters. And I will speak more about batch reactors because they provide with more chances to measure and control the parameters. And I will show this kind of things on few examples. First is a case study, synthesis and modification of simple and complex oxides, metal oxides in aqueous media. The general equation which describes this type of reactions is shown on the slide. We can see that water first, no matter what kind of reactions we are running, modification, synthesis, or something like that, or just sintering of oxides. First, we have hydration of the reactant, initial oxide, some kind of highly hydroxylated intermediate forms, and then it loses water and forms the final product or intermediate product. And we can see that water in this case acts as an active medium or even as a catalyst if we recall the classical definition of the catalyst, which is a substance which remains unchanged at the end of the reaction. And as an example, I show here some microphotographs of products formed when we treat amorphous silica in water fluids. And this is very flexible system because varying the properties of water fluid, we can produce some specific products which defined morphologies, phase compositions, surface areas, which we use then as supports for different catalysts, supported catalysts. And if we look at the dependence of the properties of the product, depending on the parameters of the water fluid, we can see that by varying a very simple parameter like density, because we can vary it by changing the amount of water which we load into the autoclave. At constant temperature, we can produce products with different surface areas, different phase compositions, and sometimes we are able to obtain very clean products in terms of morphology and phase compositions, and which are not like, for instance, cristobalite in this case, which is high temperature phase, but we can obtain it at relatively low temperature by using appropriate parameters of the water fluid. I will skip here some mechanistic slide due to the lack of the time, and move to the second case study, also very briefly. This is an example of transformation of natural organic substances and materials in water around the critical point. And we used N-hexane as a model compound. And when we open the autoclave, we have two layers of liquid, which is one of them is water layer, the second one is organic layer. Both have very complex composition, and also during the experiment we observe a kind of phenomenon which I hope doesn't work, unfortunately, in this regime. So at some point in the time, we have a break of the safety disk. Unfortunately, it's a very good movie, but it doesn't work online, unfortunately. And this is due to two phenomena. First of all, we have uncontrolled formation of gaseous products, which cannot be predicted. And the second one is very important also. As I showed you before, we have a full miscibility of water fluids with any gases and vapors above the critical point. But here we have to take into account a very important criterion, which is called the Krzyzewski criterion, which determines the pressure behavior when we mix the major component of the fluid system with some other components. And if we talk about water, all polar substances have this parameter below zero, and they decrease the pressure of water below and even above the critical point, and non-polar substances increase the pressure. And we can observe this phenomenon even when we add inert gases to water. You can see on this panel on the right bottom corner that even in the presence of not very high pressures and densities of gases like nitrogen and helium, we have pressure which is substantially higher than the pressures which can be calculated only on the basis of state equations for pure water and pure gases, and by simple adding one to another. So this is just to a very interesting and important phenomenon, which is the loosening of H bonding in water when we add non-polar components to water. So and the pressure, of course, increases in this case. But this is when we study some processes which are not very well known. This increase of pressure can be unpredictable, and we have to take into account when we plan the experiments. So here I show you very briefly how important and how not easy is the. I need maybe 2 minutes. Okay. Okay. Again, we can see that by measuring the pressure, we only not just control the safety of the experiment, but also we sometimes can kind of tracking the kinetics of the process when we have release or consumption of water. And we have several problems. One of them, always some dead and cold zones are present in the reactor. So we have difficult phenomena, like complex phenomena like uncontrolled condensation and complex convective flows in the reactor. And we need some media to separate the detectors from the medium in the reactor. But we can fight with that. I show you how we can do this on a large scale. And this is on the big body on the top is just a cover which we heat in order to prevent the condensation of water fluid. And so to conclude, I would say that this is water is a very interesting and very powerful tool for running different types of reactions. But although we are dealing with a very powerful tool, if we do not know exactly what forces and problems are standing behind this tool and how it works, we can have many problems. And further in-depth research in this field is required. At this point, I would like to thank the organization for financial support and all of you for your kind attention. Thank you very much.
Yeah, thank you very much, Professor Sinev, for the interesting presentation. I think we have time for one or maybe two very short questions. So let's see, somebody from the audience would like to ask a question? If not, then maybe I start. I was wondering actually, these problems to control, I mean, these are, we know that we can use supercritical process for gasification, for example, and so on. But wouldn't be that a way to go more or less on the completely safe side, to be completely supercritical? Wouldn't that be a solution? I have the feeling that many of the issues you mentioned come up in the moment when you have to be close to the critical point or to the border between the different phases. But maybe for the sake of simplicity, if one said I'm completely going to the other side, then one had maybe more or less control problems, let's say like that.
Yeah, you are right, completely. But it depends on the processes which of your choice. If you can choose, if you are just a pure researcher, you can choose you have a lot of choices and you can choose whatever you wish. and always we are trying to look at the area which is more, I would say, illuminated. So, and to work in the conditions which are better controlled. But if you are dealing with the practical things, and you have to run, for instance, very complex so-called one-pot processes, when you have simultaneously extraction, hydrolysis, and, for instance, hydrogenation of some specific components of complex mixtures, you have no such a choice of the range of parameters which you should work at. So it always depends on your particular needs and possibilities. So this is the trade-off always. But of course, you are completely right. Always when we are doing the experiments, we have to choose the conditions at which we obtain the more definite results. That's no doubt about it. Yeah.
Okay. Yeah. Thank you very much. I think there are many people doing hydrothermal processes are happy about somebody looking into the details here. So thank you very much once more.
Thank you very much. Thank you.
And I will take the opportunity to hand over to the second presentation this morning. It's by Professor Natalia Gavrilova from the Mendeleev University of Chemical Technology, also in Moscow in Russia. And now we will hear something about the relationship between the modes of the contactor and the extractor in a reactor with a membrane catalyst. So Professor Gavrilova, the floor is yours.
Good afternoon. Do you see a presentation?
Yes, we do. Thanks.
Okay. And good afternoon, dear colleagues. First of all, I want to thank the ORG committee for the opportunity to present our work at this conference. And let me introduce to your attention a report on an interesting area of heterogeneous catalysis in membrane reactors. The term membrane catalysis was first introduced several decades ago by academician Grisnov, whose work were pioneering on this field. Since then, the membrane reactors have attracted the attention of various research groups, and the potential advantages of their using have been shown using various chemical reactions. Some of them are presented on this slide. The design of membrane reactors may be different. The catalyst can be combined with a selective membrane made of inert materials, or itself possess separation properties. In second case, membrane catalysts combine two function, catalysis and separation, and it makes it possible to influence not only to the equilibrium of chemical reactions, but also to mass and heat exchange process in the porous catalyst structure. According to their function, membrane catalyst reactors are divided into extractor, distributor, and contactor. Majority of the studies in this area is devoted to the one of the possible mode, reactor extractor. The idea of using it to selectively remove one of the reaction products from the reaction volume. This allows to influencing the equilibrium of a chemical reactions and shifting it toward the formation of products. This leads to an increase the degree of conversion. And this type of membrane reactor is recommended to high temperature reaction involving hydrogen. And there are two other types of membrane reactor, distributor and contactor, but this mode are less studied. Our work will be focused on using a membrane reactor contactor, and this type of reactor can be of greatest interest for high temperature reaction, which are characterized by presence of diffusion limitation, and as a result of which the degree of utilization of the catalyst surface is not significant. And for many reactions, it's less than 5 or 10%. As example of such reaction, we will use the reaction of dry reforming of metal. And in a number of works, it was shown that the use even of a reactor contactor with porous membrane catalysts in the reaction of dry reforming of metal can significantly increase the productivity compared to conventional one. In our previous work was found that activity of membrane catalysts in dry reforming is several times higher than the activity of traditional catalyst in fixed bed reactor. And these results were explained by possibility of Knudsen mass transfer mechanism appearance in the porous structure of membrane catalysts. In this paper, we will present the new results of kinetic study of dry reforming of methane in membrane reactor contactor, which works in two different modes: forced mode or pressure drive mode and diffusion transport modes. At the forced transport mode, reagents mixture pass through the pore structure of the membrane catalyst due to the pressure difference. In the diffusion transport mode, the entire mixture of reagent enters and exits from shell side of reactor and penetrates into the membrane catalyst as a result of concentration difference. And these results will be compared to reactor extractor. A scheme of reactors, flows, and some reaction condition are presented on this slide. First of all, it's necessary to note a comparison of two reactors with traditional catalyst and membrane catalysts under dry reforming condition. The results you can see on the slide. Under the same condition on catalyst of the same chemical composition, the conversion rate were compared. At the same conversion rates, the contact time on membrane and conventional catalyst differ by an order of magnitude. On a membrane catalyst, the contact time is 40 times shorter than a traditional one, and that is dry reforming in a membrane reactor proceeds at much higher rate. We also compared two modes of contactor with diffusion and force transport. And as you can see in this graph, regardless of the reagent transport mode, characterized by pressure drop at the reactor inlet, the methane conversion rates are close. And since dry reforming of methane is an endothermic process, the temperature of the gas medium on both sides of the membrane catalyst were monitoring during all experiments. And as you can see on this graph, these temperatures were different. The temperature inside the membrane catalyst were lower than in an annual space of the reactor. Small difference in the value of the rate constant in membrane reactor contactor with two different modes grounds to assume that in both contactors modes, driving forces of similar magnitude and origin act, causing the transport of reagents through the porous structure of the membrane catalyst. In order to make sure that the reaction mechanism remains the same, the following dependence was presented. The dependence of the change in the concentration of all components of the reaction on the consumption of methane confirm the complete identity of the chemical and transport stage in both modes of membrane reactor. For all components of the reaction mixture in both modes of the membrane reactor, the concentration lie on the same trend lines than you can see on this figure. The results of carbon dioxide conversion of methane in the extractor mode are shown in the slide. Despite the fact that the concentration of substances change in the streams of retened and permeate, the degree of methane conversion remains practically unchanged in the entire range of permeate and retentant. This can be explained by the structure of the flow that occurs in the channels of the catalytic layer under the condition of non-isothermal Knudsen diffusion. It's known that as a result of gas dispersion in a porous medium, with pore size smaller than the mean free path of molecules, the free molecular mode of transport can be realized. The mode of transport in the pore can be estimated from the Knudsen number, which characterizes the ratio of the mean free path of molecules of the characteristic pore size. For example, the average diameter of catalysts. This value of Knudsen number determined for several catalysts are given in this table. As you can see, the Knudsen number of membrane catalyst is more than 10, so a free molecular flow of Knudsen diffusion is really observed. In the stationary process of carbon dioxide conversion, non-isothermal Knudsen diffusion appears, which is characterized by appearance of unusual phenomena. First, the channels of the porous structure, its circulation contour arises in which one flow, thermal creep, obeys the law of gas dynamic, and the second, viscous flow, obeys the hydrodynamic of continuous media. And under this condition, the reaction mixture passing through the reactor is exposed to multiply contacts with the catalytic surface, which increase the flow of reagent and increase the reaction rate constant. This phenomenon is widely used in various macroelectronic devices, and the most famous is the Knudsen compression. And the flow structure of the membrane catalyst and compression is identical. And in previous studies, we made sure that the membrane reactor can work as a Knudsen compression. So the above approach to analysis of mass transfer of different mode of membrane reactors with the membrane catalysis show the key role of mass transfer process is in intensification by the example of dry reforming of metal. In the kinetic experiments, the magnitude of the flux can be determined from the material or heat balances of the reactor. And thank you for your attention.
Yeah, many thanks, Professor Gavrilova, for the presentation. Yeah, now we have decent time for discussion, so maybe there are questions from the audience. Maybe to warm up the discussion a little bit. Actually, I'm definitely not a specialist in your field, so the question I had, if you do the dry reforming of methane and CO2, and then you do it inside the membrane, at the end, your main product, which is the CO and the hydrogen, go out on the other side, right? Would that be rather kind of an extractor type of behavior where we actually use the selective separation of the reaction products to shift the equilibrium?
Yes, yes. Membrane reactor in extractor mode possesses a selective separation, and it can be influenced to the equilibrium of chemical reaction.
Yeah, yeah. Because then for me the concept of a contactor versus a extractor, but the difference is not so clear for me in that case, because you said this is a contactor, but I had the feeling it works like an extractor. That is right. So in principle, we remove D, right?
This difference can be seen from this figure, and if we use extractor mode, gas mixture, it's these flows, and catalytic selective layer can separate the gas mixture, and one of the product can leave the reaction mixture at the other side of membrane.
Yeah, yeah.
if we use a contactor, all gas mixture go through the catalytic layer, and in the reaction condition appears a new effects caused by Knudsen diffusion appears. So this mixture can multiply, contact the catalytic sites, and it possesses a more effective use of catalytic material.
Ah, okay. And now for the experiments, can you a little bit tell us which materials you use? What is the membrane and what is the catalyst in your experiments?
Yes. Membrane catalyst is a composite material that consists of two different materials support. It's a tubular microfiltration membrane based on alpha aluminum oxide, and catalytic layer was molybdenum carbide.
Okay, so the catalyst is only on the outside.
The catalyst on the one side of membrane.
Yeah, okay, the outer side. Okay, very good. Okay, and did you have any problems with carbon formation? Something like deactivation of the catalyst or so?
When we use a membrane catalyst, we can and this reaction can be occurs at more lower temperature. In that temperature region, carbon deposition is not observed.
Okay, so that would be also a nice additional feature that we avoid the carbon deposition here.
Yes.
Okay. Okay, are there more questions from the audience maybe? So far, no further questions. Then maybe I have one more before we go over to the next presentation. You had this forced mode and the diffusion mode. Now my question, maybe I'm not sure whether I understood this correctly. In the forced mode, you have more pressure on the outside than inside, right? So the gas needs to go through the system. And in the other mode, most probably the pressure difference is smaller. But wouldn't we then expect a lot of back diffusion? That the reaction products move back on the reactant side?
We use two different modes that can be realized in a membrane contactor. At the forced transport mode, reagent mixture passes through the pore structure of membrane due to pressure difference. And the other mode, diffusion transport mode, mixture of reagent enters and exists from shell side of catalyst and penetrates into the membrane as a result of concentration difference.
Ah, okay. And then you change between the two modes?
Yes.
After time. Okay, that's the trick. Okay. Thank you very much.
Thank you very much.
So I think, yeah, then time is over now and we would go over to the next presentation. Thank you very much, Professor Gavrilova. Okay, and then we can go ahead. Yeah, we're a little bit early, but that gives you a little bit more space then. So it's my big pleasure to introduce Professor Enrico Tronconi from the Politecnico di Milano. And he will give a presentation actually very similar to the topic which we had also yesterday in one of the keynote lectures: electrified steam reforming, resistive wash-coated silicon carbide foams as internal heating elements for the hydrogen production. So Professor Tronconi, the floor is yours.
Thank you, Tilman, for the introduction, and good day, ladies and gentlemen, dear colleagues. It's a pleasure to be here with you today. So my talk deals with a new reactor concept for the electrification of methane steam reforming, and is based on the direct Joule heating of structured cellular internals like open cell forms, wash-coated with a rhodium-based catalyst. So the reasons why electrification of chemical processes is rapidly becoming a hot topic of research nowadays have already been clearly presented by several speakers in this conference, including Professor Guy Marin, Dr. Roberto Zennaro, and most of all, Professor Ib Charkendorf in their plenary lectures. So we are all aware that there is a dramatic increase of electric energy from renewable energy sources, both in Europe and in the US. And this, of course, has a positive effect on the reduction of the CO2 emissions, but also it represents an opportunity for the chemical and process industry in view of converting this excess energy into valuable products according to the so-called power to X concept. And certainly a most attractive approach in power to X applications is the direct conversion of electricity into green, clean hydrogen via water splitting in electrolyzers at the cost of approximately 4 kilowatt-hour per cubic meter of hydrogen. And the hydrogen, of course, can then be converted into valuable products in subsequent catalytic reactions. But we know also that electrolysis is not the only options we have to convert electric energy into useful chemical products. A very interesting alternative is the use of electric energy to supply the heat of reaction to the endothermic methane steam reforming process, as presented by Professor Charkendorf in his brilliant plenary lecture yesterday. There are several advantages in doing so. By replacing the radiative heat supply in conventional fired reformers with electric heating, we completely eliminate the CO2 emissions from fuel combustion, which is typically at least 30–40% of the total CO2 emissions of the reformer. Also, by removing the firebox, we substantially reduce the footprint of the reformer plant. Moreover, by bringing the heat supply very close to the catalytic site, we reduce the heat transfer limitations, which are the bottleneck of the conventional steam reforming process, paving the way to process intensification for the development, for example, of compact reformer units. Finally, this technology is also easy to integrate in existing process layouts, grants flexibility, and very interestingly, also fast dynamics. And last but not least, the specific power consumption per normal cubic meter of hydrogen produced is remarkably less than in electrolyzers. From a reactor engineering perspective, however, which is the perspective which really matters in this conference, the question is, how do we implement the Joule heating of the reformer? The solution, which was illustrated yesterday by Professor Charkendorf, involves direct ohmic heating of the wash-coated reactor tubes or channels. As discussed yesterday, this does ensure excellent heat transfer to the catalyst. On the other hand, the performance of a reformer with wall-coated tubes is eventually controlled by external diffusion, gas-solid mass transfer, which calls for the adoption of tubes with small diameters, leading eventually to the development of a reactor solution which is based on either honeycomb monoliths or microchannel technologies. In Milano, we are working on an alternative solution for the electrification of steam reformer, which is based on the direct Joule heating of open cell foams, also known as sponges, so cellular materials. And in previous work, we have assessed by combining experimental and computational approaches the superior mass transfer properties of such substrates in comparison to laminar flow in straight monolith channels. So once we catalytically activate the foams by wash coating, for example, the superior mass transfer properties would enable the direct utilization of these materials after direct joule heating is applied to their continuous thermally and electrically connected structure to provide a significant intensification of the reformer performances, enabling, for example, the design of compact units for distributed hydrogen applications. So we have been exploring this concept experimentally, and open cell foams actually are commercially available in a variety of ceramic and metallic materials. So a first question here is to select the foam fabrication material. We focused first on the electrical properties requirements, and our preliminary analysis revealed that the material of choice should actually have an electrical resistivity in a very narrow range to enable reasonable currents and voltages for joule heating. Now, for example, metals have electrical resistances which are far too low in our view. They would require exceedingly high currents. On the other hand, we found from our preliminary heating tests that silicon carbide foams or honeycombs actually exhibit optimal electrical resistances. And this is not surprising because silicon carbide is used for the manufacturing of heating elements in commercial heating elements in electrically heated furnaces, for example. And silicon carbide is also very interesting in view of its excellent thermal conductivity, which is much higher than stainless steel. So here we show the preliminary reactor layout that we have been using in our experimental investigation, starting from non-reactive heat transfer experiments. The system is based on a silicon carbide foam connected to a DC power generator, and the connectors are made with copper tubings welded to stainless steel plates with holes to enable the flow through. And the two plates are pressed onto high pore density copper foams to reduce the electrical contact resistance. And then we have the wash-coated foam, which is electrically insulated by a dense alumina tube and is placed inside a stainless steel tube acting as a pressure shell. Outside, we have also a thermal insulation layer. And we measure the temperature at the outlet of the foam by a thermocouple insulated by an alumina tube. To make the silicon carbide foam catalytically active, we wash coat it with an active homemade rhodium on alumina catalyst formulation. Partially, we wash coat only about 3/5 of the whole catalyst sample. The initial part is used for preheating purposes. The overall catalyst loading is in the order of 2.2 grams, so 55 grams per liter for our foam sample. And this was obtained by 7 replicated processes of deep coating and spin coating according to a procedure that we have developed in our labs. As shown by the SEM images on the left, we were able to achieve a reasonably good homogeneous coverage of the catalytic foam without any evidence of pore clogging phenomena. So we placed the silicon carbide foam wash coated with the rhodium on alumina catalyst inside our tubular stainless steel reactor. So the feed gas was preheated in the uncoated upper part of the foam, and the methane steam reforming reaction proceeded in the downstream wash coated portion of the catalyst sample. We ran blank experiments initially over an empty silicon carbide foam to rule out any methane conversion up to 750 degrees C. Prior to any catalytic activity test, we condition the catalyst, and then we run catalytic activity experiments at ambient pressure at two different space velocities with a steam to carbon ratio of 4:1. And we operated the reactor at different outlet temperatures that were obtained by simply adjusting the input voltage of the power supply. Here are some results. Methane conversions are plotted against the outlet temperature measured at the exit of the catalytic foam. And you can see here that as a result of a strongly reduced heat and mass transfer resistances, we were able to achieve methane conversions approaching the equilibrium curve across a full range of conditions. And actually, we reached essentially a complete methane conversion at temperatures above 700 degrees C. And we have replotted the methane conversions against the input electric power in the figure on the right-hand side, just to better appreciate the overall input-output relationship in our experiments. Of course, we are new to the field. We have never run electrified steam reforming experiments before, so we are particularly curious about the electrical parameters affecting our catalytic experiments. The plot shown here on the left shows that we observed essentially a linear correlation between the measured outlet temperature and the corresponding input power. And this is in agreement with the almost constant electrical resistance of the silicon carbide foam across the whole temperature range that we have covered. Moreover, the electrical resistivity that we have estimated from our experiment is around 0.04 ohms per centimeter, which is in the range of typical values reported for commercial silicon carbide heating elements, which is kind of reassuring for us because it seems to indicate that the proposed that our experimental setup is working without the presence of additional undesired contact resistances. Of course, heat losses are an issue in this kind of experiments due to heat conduction across the stainless steel tube wall in spite of the insulation layer that we have included. So we estimated the power losses in our experiment by subtracting the process enthalpy gain from the input power. And we find that the power loss is essentially proportional to the temperature at the outlet of the reactor, but is independent of the gas feed flow, which means that the energy efficiency instead grows with space velocity, with increasing space velocity. We did some calculations to evaluate the energetic performances of our system. And we found that the highest energy efficiency was something like 60%, corresponding to a very low power consumption per unit hydrogen production, limited to about 2 kilowatt-hour per normal cubic meter of hydrogen, which is markedly lower than the specific power consumption typically reported for industrial electrolyzers. In parallel to our experimental activities, we have run also modeling work. We have developed a simple two-dimensional heterogeneous reactor model of our electrified steam reformer. We have used rate expressions derived from our recent kinetic investigation of methane steam reforming over the same rhodium-based catalyst tested under concentrated conditions. And for the estimation of the heat and mass transfer coefficients, on the other hand, we have used the engineering correlations that we have derived during our previous fundamental study of the transport properties of open cell foams as enhanced catalyst carriers. Here we show some results of model simulations. that we have run considering a hypothetical compact reformer for distributed hydrogen generation, a very small scale unit with a foam 10 centimeter in diameter and 20 centimeter in depth. Actually, the simulations show that this system can indeed be operated at very high space velocities, much higher than in the case of the industrial reformers, with very, very limited interface gradients. We predict only very small differences between the gas and the solid temperature and concentrations, and also limited deviations from the equilibrium conversion. And this result is basically due to the very high activity of the catalyst, but most of all to the enhanced heat and mass transport properties of the foams that we are adopting. We have also run some comparative simulations assuming both honeycomb monoliths and foams. I will not go into the details of these results for the interest of time, but I will just mention that in general, in the case of the honeycomb, both internal limitations and internal mass transfer limitations are more severe than in the case of foams. So coming to the conclusions, in summary, hopefully we have been able to demonstrate experimentally the feasibility of running the methane steam reforming reaction over a Joule-heated wash-coated foam catalyst. And the initial performances that we have been observing in our lab scale setup promise high hydrogen productivities, high energy efficiency, and low specific power consumptions, thanks to the transport properties of the foams. And these data also, according to the modeling results, seem promising in view of compact electrified reformers for distributed small-scale applications. And just before closing, let me just mention in passing that, as discussed yesterday already, the same reactor concept is applicable, at least in principle, to the electrification of other endothermic processes, which are quite relevant for power-to-X technologies and in general for the chemical energy sectors, like, for example, the reverse water gas shift reaction, the ammonia cracking, dehydrogenation and cracking reactions, and also other possible processes. So I would like just to acknowledge the financial support from the European Research Council, a sincere thanks to all the members of the catalysis group in Milano. This is a picture taken during the meeting of the Italian Catalysis Society in Milano a few years back. And of course, thank you all for your kind attention. I hope there is still time for some questions.
Yeah, thank you very much for this very fascinating talk. And indeed, we have about 2 minutes left over for questions. So the talk is open. And I see Professor Sinev raising his hand. So yeah, please, Professor Sinev.
Physically, not virtually. Thank you very much. Thank you very much, Professor Tronconi, for your very interesting presentation.
Thank you.
I have a question. During the whole your talk, I asked myself, what is the temperature distribution inside your foam? You showed us the results of calculations on one of your last slides, but did you measure those distributions physically, not only axial, but also radial? Because knowing the distribution of temperature, you may also somehow optimize the distribution of catalyst in the system or something. At least there are some interesting features of how reaction proceeds also can be extracted from this.
I totally agree, and thank you for this very important and insightful remark. We totally agree. So far, we have not been able to measure the temperature distribution in our systems. We are getting to that. We are planning to develop a setup which enables us to do so. You're totally right. We can expect in principle these uniformities in the temperature distribution. We actually know that other people have been able to observe this in Joule heating of cellular structures like foams. I mentioned commercial foams. In principle, they are not perfectly uniform in their geometry. So we expect that this might result also in a non-uniform distribution of the current, and therefore also in non-uniform distribution of the temperature. So we might have hot spots and cold spots in the structure. This is one reason, by the way, why we are planning to look. Actually, we are already looking into another class of cellular structures, which are the so-called POCs, printed periodic open cellular structures. These are 3D printed materials, still cellular materials, but with manufactured by 3D printing according to a very regular and very well controlled geometry. And this would ensure, in our hopes at least, a very uniform distribution of the current in the cellular structure, and therefore also more uniform temperature distribution. But you're totally right, we need to measure the temperature distribution. This is something that we are going to do in the near future.
Okay, dear colleagues, unfortunately, we have to proceed to the next presentation, but I would really like to thank you once more for the indeed very fascinating presentation. We have seen the paper is on the way, and also thank you very much for the good discussion from the audience. Thank you very much, Professor.
Thank you, Tilman. Thank you.
Okay, now we stay in the heat transfer topic. So the next presentation is on heat transfer in slender packed bed reactors, and there's a main focus on the effect of radiation, and it's presented by Professor Gregor Wehinger from Universität Clausthal. So Professor Wehinger, the floor is yours.
Yeah, thank you, Mr. Schildhauer, for this introduction. I'm glad to present to you today a topic entitled Heat Transfer in Slender Packed Bed Reactors, Effect of Radiation. So, as we seen here in this discussion for the last couple of minutes, radial heat transfer is actually pretty challenging, especially for the classical applications in packed bed reactors, as you can see on the right hand side. So basically, this radial heat transfer is most challenging aspect of a safe, stable, and economic operation of catalytic packed bed reactors. For highly exothermic or endothermic reactions, we typically have slender packed beds with a tube to particle diameter ratio pretty much smaller than 10. This is due to we want to have a low pressure drop, high heat transfer rates, etc. However, for these slender packed beds, we typically observe local bed structures that significantly influences the local heat transfer transport phenomena. And in addition, for very high temperature processes, we typically also observe thermal radiation effects. So the pseudo-homogeneous models that are mostly used in design phase are rather questionable. So in this study, we wanted to reveal new insights of packed bed reactor heat transfer without chemical reaction this time, with the so-called particle-resolved computational fluid dynamics approach, PRCFD, which you can see on the right-hand side. So basically in this modeling approach, the very detailed modeling approach, we resolve each and every pellet inside a reactor tube and model the gas phase around the particles, as well as, in this case, only heat transfer through the solid pellet. And the scope of the study was to, first of all, carry out PRCFD simulations, including and excluding thermal radiation effects for packed bed of spheres and packed bed of rings. Then quantify thermal radiation effects depending on the particle Reynolds number, as well as 3 different temperature levels. And then compare these PRCFD results with the pseudo-homogeneous model in order to draw conclusions. So here I show you the 2 different packed bed geometries. So we synthetically generated these packed beds, as you can see here, the packed bed of spheres with the Blender workflow that we published years ago. So these are 1,000 spheres with 5 mm diameter. and we have a D by D ratio of around 5. On the other hand, we have 1,000 rings generated. Here is a packed bed, also with 5 millimeter diameter and height. But since the stacking is a little bit different, the length of this bed of rings is also a bit higher than the bed of spheres. But both of them are 1,000 particles included. Then in the next slides, the flow is typically from left to right. I included for the CFD simulations an entrance region and outlet region, just in order to minimize these effects on the transport phenomena inside the packed bed. Then I, as I already said, modeled fluid phase as well as the solid phase in the CFD approach. As you can see here, the computational mesh, because obviously we don't have an analytical solution for that, so we solve for the Navier-Stokes equations in the gas phase, as well as thermal conduction in the solid phase, coupled now with the conjugate heat transfer model. And we have roughly about 22, 21 million cells, so pretty large computational mesh. And this takes a while in order to converge. So on the right-hand side, I just got a quick summary of the boundary conditions. As I said, we investigated 3 different particle Reynolds numbers, as you can see here. 306, this one corresponds to a 1 meter per second superficial velocity. Then we also looked into a little bit higher velocities, resulting in particle Reynolds number 1,000, so turbulent regime, and 2,000. On the other hand, we looked at 3 different temperature ranges, namely the temperature range is always a constant between the inlet T0 and wall TW. And we investigated 300, 400 centigrades, 400, 500, so milder conditions, and then 700, 800 centigrades, which are typically found, for example, in steam or dry reforming conditions. And then we kept the gas phase as well as solid phase properties constant, just in order to better compare the results. Surface to surface radiation was then taken into account. So that means the solid particles irradiate thermal radiation to neighboring particles with the so-called ray tracing method included in Siemens SimCenter star CCM+. So let's go to the results. Here I show you some qualitative results. As I said, flow is from left to right, and we see that the picture on the above is a cut through the bed, and we see that the fluid as well as solid is heated up unregularly. So sometimes we can identify certain particles, but then at the very end, we are very close to the wall temperature. Here we see the surface temperatures of the packed bed with and without thermal radiation for the same conditions. And as you might notice, we already see some hotter particles already at the beginning or in the first third of the particle packed bed. So that means this thermal radiation is an extra heat transfer mechanism. And on the bottom, you see a typical velocity magnitude distribution. So we see acceleration zones in the near wall region. So this is this wall channeling that you might know. And then in pretty close, where particles are pretty close together, we sometimes see velocities pretty much approaching 0. So we have stagnation regions here. So really complex. And it's even more complex for the packed bed of rings, as you might see here. But once again, this thermal radiation plays a significant role as an additional heat transfer mechanism, especially where the temperature gradients are pretty high. So let's move on to the quantitative results. So on the left-hand side, I show you 4 the different particle Reynolds numbers. Now the axial temperature profile from the CFD simulations. Blue is the scenario without radiation. And then the reddish ones are the scenarios for the 3 different temperature levels. So basically, and this is what we assumed, we have a stronger effect of thermal radiation the higher the temperature level is, obviously. This is the Boltzmann law included. But the extent depends on particle Reynolds number, although thermal radiation is independent on the velocity. It interacts with the occurring transport phenomena. And this is also what we can see here. So here, it's a cross-section on this dotted line for the 3 different particle Reynolds numbers. And now on these rows, you see for the different temperature levels now the difference between the scenario with radiation and without radiation. And as you might notice, we see very large differences. Largest one is around 40 Kelvin for the scenario lowest velocity and highest temperature range. But on the other hand, we also can see for the high velocity range that the effect of thermal radiation is highest very close to the wall. So the hot wall is influencing the near wall particles. The same is true for the rings. And now, as you might notice, the scenarios look a little bit different or look a little bit more complex, but still we can conclude that the highest effect is close to the wall. Then I want to give you an idea about how the azimuthal distribution looks like. So that means on 3 different levels inside the bed, I draw you in black the average velocity, the average temperature, as well as all of the temperatures on this cross section. And as you might see, we have pretty large interquartile ranges, ranging from 5 to even 11, very close to the wall. So in other words, although we see here this average value, we still have a large distribution at a certain point due to the azimuth differences. So this has to be kept in mind when I go to now the next investigation. That means the difference between PRCFD and the 2D modeling approach. So here I give you the equation of this famous 2D pseudo-homogeneous model where we solve for the temperature in axial as well as radial direction with 2 factors now, 2 parameters. One is the effective radial thermal conductivity, and the other one is the apparent wall heat transfer coefficient, HW, which then results in a Nusselt wall at this typical boundary condition of the wall. So we now derived from our PRCFD simulations these 2 parameters, K effective R and HW, according to a method suggested by Wakao and Kugai in the 1980s, where we actually plot the axial profile, now this from the CFD simulation, as you can see here, in a logarithmic way. And then we're going to fit a straight line to a certain amount of this curve. And finally, we have a slope and the intercept. And depending on method 1 or method 2, we use the slope and a Bessel function, which I skip here. And method 2 only uses the slope and the intercept here. So both methods I will compare in the next slides. So the derived heat transfer parameters represented as Nusselt wall and K effective by K fluid looks like that. So dots are the scenario CFD without radiation and stars are with radiation. And I compared that with typical correlations for Nusselt wall against Martin-Nilles. And for both cases, we can see that Martin-Nilles is highly underpredicting the thermal radiation effect, especially for higher Reynolds numbers and higher temperature levels. On the other hand, the K effective from Zehner-Bauer-Schlinder looks, at least for method 1, pretty good, I would say. Method 2 somehow gives different values, but I will come to that later on. For the rings, the situation looks a little bit different. This might be that that lateral mixing is more pronounced in the packed bed of rings. That means the thermal radiation effects are a bit minor. This is what you can see here. Here I really compare the PRCFD results with the 2D heat transfer model for radial temperature profiles at different positions. So the dots are the CFD simulations, and a straight line now is a 2D pseudo-homogeneous model with the derived parameters. And as you can see for the spheres, the model with parameters method 1 looks pretty good. Here on a parity plot, we are really close to the PRCFD results, obviously not very close to the wall, because here we see this temperature jump. On the other hand, for the rings, both methods give more or less the same radial temperature profiles. However, we see a pretty large deviation between this pseudo-homogeneous model and the PRCFD simulation. Obviously, this wavy contour cannot be captured by the model, but on the other hand, we also see deviations in the bed center as well as really close to the wall. The parity plot reveals that. So let me conclude my talk. I showed you in a theoretical study that thermal radiation contributes substantially to the overall heat transfer in packed beds, even below 400 centigrades, where we typically do not estimate that or suggest that. The largest contribution in this scenario, hot wall cold fluid, is in the near wall region until approximately 1 particle diameter away from the wall, which is then represented by this Nusselt wall rather than the K-effective radial. However, the typical correlation of Nusselt wall rather underestimates the thermal radiation effects. Minor effects can be seen in the bulk. But we also have to keep in mind that in a CFD simulation, we still see some huge differences, temperature differences, depending on where you are on your cross-section. But definitely we need a broader picture, especially for even lower D by D ratios and different particle shapes, because then obviously thermal radiation might play a more severe role. And we also have some additional parameters influencing this effect, namely thermal conductivity, emissivity values, and obviously we need experimental validations. So with this, I want to thank you for your attention and BASF for financial support. Thanks.
Yeah, thank you, Professor Wegener, for this, again, also very fascinating talk, a lot of interesting things to look at and to understand. So the talk is open for discussion. The questions from the audience. And maybe to warm up, I start with one. Actually, when you showed these graphs on where we see the temperature distribution over the particles, then I had the feeling that you always showed with radiation, without radiation. It was mostly the one, that one. And if I look on the spheres, then the difference between with and without is not that strong. But actually, if you go to the rings, it was, in my eyes, a stronger effect where we see earlier the onset of that phase. For example, where you see the complete cross section being already yellow, that is most probably 2 centimeters earlier. So I have an idea of why that is, but maybe could you comment on that one?
Mm-hmm. So the thermal radiation effect, as I said, depends obviously on the temperature level as well as on the area that is irradiated by this hot reactor wall, as well as then on the Reynolds number. So depending on these 3 aspects, we see different influences. And this the particle shape and the Reynolds number, this is obviously plays then an important role for lateral mixing, which also then influences on that. And this one here for the rings, as you can see here, once again, the influence is not that strong. Might also be that the overall porosity in the bed of rings is much larger than for the spheres. Yeah, but I don't know what point you thought
No,
of.
my feeling was because there's less of the packings or the particles making shadow on the other ones, right? There's this option to have iteration more or less in the middle. If it is oriented the right way, that might have an effect. So it actually would be interesting to have a structure which keeps way more open area that the radiation can actually penetrate deeper into the reactor. That would be a kind of an idea to test it.
Yeah, exactly. This penetration depth is definitely worth investigating. And yeah, for the smaller D by D ratio, this might be even more deeper, let's say. Yeah. Mm-hmm.
Okay, so if there's another short question from the audience.
May I ask a question?
Yeah, please.
Thank you for the very nice talk. I was wondering whether you expect any impact of the thermal conductivity of the pellets on the effect of the radiation. So assuming that you have a pellet with a very, very high thermal conductivity, do you expect this effect of thermal radiation to be less?
Yes. I expect so. Because when we think of contributing or the different contributions of radiation, conduction, convection to the overall heat transport, obviously if there is less, if the thermal conductivity is lower, then thermal radiation is a higher driver, larger driver. However, if the thermal conductivity is very high, for example, full metal particles, then probably this thermal radiation effect is a little bit minor. Yeah. So here I used rather low values of the solid, 0.25 watt per meter Kelvin. So this is typically highly porous catalytic material. I also tested 2.5, and then the effect was a little bit lower than with this very low thermal conductivity. Yeah. So yeah, this is true. Yeah.
Thank you.
Okay, thank you very much for the interesting discussion, and once again, Professor Wenger, for your presentation. And then I think we should move to the next one. The next presentation is given by Dr. Guillermo Díaz-Sainz from the University of Cantabria in Santander in Spain. And we will hear about a filter press reactor with a continuous electrocatalytic reaction of CO2. So Dr. Díaz-Sainz, the floor is yours.
Okay, I'm going to share my screen. Can you listen to me? Can you see my screen?
Yeah, everything works perfectly. Thanks.
Okay, perfect. Thank you very much for the very introduction. First of all, I would like to acknowledge to the organizing committee of this International Conference of Chemical Reactors to give us the opportunity to make this oral communication entitled Filter Press Reactor for the Continuous Electrocatalytic Reduction of Carbon Dioxide to Formate using bismuth-based electrodes, work developed in the Chemical and Biomolecular Engineering Department at the University of Cantabria and in collaboration with the Institute for Electrochemistry of the University of Alicante. About the content of the presentation, we start with a very brief introduction and motivation of the work. Well, the carbon dioxide emissions to the atmosphere has continuously increasing since the Industrial Revolution due to the burning of fossil fuel for the energy production and for the transport. Recent, the concentration of carbon dioxide in the atmosphere has reached the value of 420 parts per million. So for this reason, there is an urgent need for developing some strategies to reduce the carbon dioxide emissions to the atmosphere and mitigate climate change. Apart from the improvement of the energy efficiency of the process and change the energy for the energy production of fossil fuels from renewable sources of energy, the electroreduction of carbon dioxide to value-added products has been converted into an interesting option and promising option for storing energy from renewable and intermittent sources of energy, such as wind or solar energy, and because we can obtain different value-added chemical products. In this context, the formic acid or formate has been considered as an interesting product obtained by the CO2 electroreduction because it could be used as a fuel cells, reactant in low temperature fuel cells, as well as a hydrogen promising carrier molecule. In addition, the formic acid could be used in several industries as a raw material, such as in the agri-food industry, in the textile industry, and as in the rubber manufacture and leather processing. In general, the formic acid production has reached a production of 800,000 tons per year, a market of $430 million, and a price that can be reached $1,200 per ton. In this context, it is very important to remark that recently a lot of study has been published in the literature using bismuth electrocatalyst in the cathode for the electrocatalytic reduction of carbon dioxide to formate, because it could be considered that the use of bismuth it has been observed that the use of bismuth has reduced the overpotential compared with other electrocatalysts, such as, for example, the lead, tin, or indium. And in addition, there is some problems in this kind of process associated with the low solubility of carbon dioxide in liquid electrolytes. For this reason, in the last years, there is a lot of approaches using a carbon dioxide unified input stream in order to avoid the problems associated with the low solubility limitation in the liquid electrolytes. In this context, the main aim of this work is to analyze the performance of bismuth-based electrodes with the configuration so-called catalyst coating membrane electrodes, CCMs, in which the catalyst, in this case the bismuth carbon-supported nanoparticles, is deposited entirely over the membrane naphthalene for the continuous electrocatalytic reduction of carbon dioxide to form it in a filter-press electrochemical reactor. It is important to highlight that in this case the membrane acts as a solid polymer electrolyte. In addition, the influence of some key variables of the process, such as the temperature, the amount of water in the carbon dioxide humidified input stream, the amount of bismuth carbon-supported nanoparticles over the electrode surface, and the current density were studied for the electrocatalytic reduction of carbon dioxide to formate. In addition, this study was published recently in XXIV Journal, in an article published in XXIV Journal. About the methodology, this section is divided in, firstly, we explain the experimental setup configuration, the filter press reactor configuration, and the cathode configuration, in which we use a catalyst coating membrane electrode, and finally, we explain the figures of merit used for assess the performance of the electrode reduction of CO2 to formate. We start with experimental setup configuration. The key element of the experimental setup is the filter press reactor, in which is a two-compartment electrochemical reactor. On the one hand, we use anolyte aqueous stream, that is a potassium hydroxide solution with a concentration of 1 molar with a flow rate constant of 5.7 milliliters per minute. On the other hand, the input or the feed at the cathode side of the electrochemical reactor is a carbon dioxide humidified input stream using a vapor delivery module, which allows control the flow of carbon dioxide, the flow of water, and the temperature. Finally, the current density supplied to the electrochemical reactor is given by a potential galvanostat. We focus on the filter press reactor configuration. The key elements of this filter press reactor configuration are, on the one hand, the dimensional stable anode, that is a DCA, which favors the production of oxygen, and on the other hand, the key element of the reactor is the catalyst coating membrane electrode, CCM, which acts as an electrocatalytic support, which acts as a separator of both compartments, and at the same time as a solid polymer electrolyte. The catalyst coating membrane electrode contains 2 layers. The first one, the naphthalene membrane, that acts as an electrocatalytic support, and over this membrane we deposited by a Bruce techniques the catalytic layer, that is a mix of bismuth carbon-supported nanoparticles, naphthalene that acts as a binder, and the isopropanol that acts as a solvent. The electrocatalysts are using the bismuth carbon-supported nanoparticles, which are an average size of 10 nanometers approximately, which are synthesized and characterized by the Institute of Electrochemistry of the University of Alicante. If we focus on the figures of merit, the different figures of merit were used to assess the performance of the process, and apart from the formate concentration, which is analyzed in the output stream of the cathode side of the electrochemical reactor, we use the energy consumption, that is the amount of energy used to produce the target product, that is the formate, the Farad efficiency for formate, that is the percentage of the total charge supply that is used to obtain the formate, and finally the formate rate, that is the production of this product, the formate, per unit of area and time. It is important to note that the area of the electrode used in this work are 10 square centimeters. If we focus on the results, this section is divided into the influence of the different key variables that are explained in the objective section. We will start firstly with the influence of temperature, with the influence of the water flow in the carbon dioxide stream, the influence of the bismuth catalyst loading, and the influence of the current density. If we start with the influence of the temperature, all the experiments were carried out with a bismuth catalyst loading of 0.75 milligram per square centimeter and current density of 45 milliampere per square centimeter, and a relative humidity in the carbon dioxide humidified input stream of 100%. Several tests were carried out in a range of temperature between 20 Celsius degrees or ambient conditions of temperature and 50 Celsius degrees. We can observe that increasing the temperature from 20 to 50 Celsius degrees, all the figures of merit used for assess the performance of the process, that are the formate rate, formate concentration, energy consumption, and Farad efficiency, were damaged, and for this reason, the best temperature used for the electrocatalytic reduction of carbon dioxide to formate was 20 Celsius degrees, and for this reason, the next sections, all the experiments were carried out at this temperature. About the influence of the water flow in the carbon dioxide stream, the same bismuth catalyst loading and the same current density values in compared with the influence of temperature was used. In this case, we can observe that working with a water flow in the carbon dioxide stream of 0.5 grams per hour, a formate rate of approximately 1.3 millimole per square meter per second, and a Farad efficiency for formate of 55% was obtained, and at the same time, in this same value, a formate concentration of 26 grams per liter with an energy consumption of only 950 megajoule per kilomole. In addition, we can observe that increasing the water flow from this point to 1 gram per hour, we can observe that all the figures of merit, the formate rate, Farad efficiency, energy consumption, and formate concentration were worsening, and this is because the amount of water introduced in the carbon dioxide humidified input stream were diluted with the water used. For this reason, the formate were diluted. About the influence of the bismuth catalyst loading, in this section, we studied the influence of doubling the catalyst loading from 0.75 to 1.5 milligram per square centimeter, and the current density used for this experiment was 45 milliampere per square centimeter and temperature value of 26 degrees. That is considered the optimal value for the electrocatalytic reduction of carbon dioxide to formate. We can observe that working with a catalyst loading of 1.5 milligram per square centimeter, the optimal value of water flow is 3 grams per hour, obtaining Farad efficiency for formate of approximately 72% and formate concentration of 34 grams per liter. It is important to highlight that increasing in general the bismuth catalyst loading, it is needed to increase the amount of water in the carbon dioxide humidified input stream, because it is necessary to achieve a trade-off between the gas liquid solid reaction system equilibrium. And finally, the influence of the current density. In this section, all experiments were carried out with the bismuth catalyst loading, water flow, and temperature that are considered optimal in the previous sections. We can observe that increasing the current density from 45 to 200 milliampere per square centimeter, the formate concentration increases at the values up to 46 grams per liter, sorry, but at expense of decreasing all the other figures of merit, that are the Farad efficiency, and increasing the energy consumption, achieving values of 1,400 megajoule per kilomole. About the main conclusions and final remarks of this work, it is important to note that a continuous gas phase electroreduction of carbon dioxide to formate was studied to avoid the use of a liquid catholyte using an innovative configuration of electrode that acts as an electrocatalytic support, separator of both compartments, and in addition as a solid polymer electrolyte. In addition, bismuth carbon-supported nanoparticles are used as electrocatalysts in the form of catalytic coated membrane electroconfiguration, and some key variables are studied, that is the temperature, the amount of water in the carbon dioxide humidified input stream, the bismuth catalyst loading, and the current density, and forming concentrations up to 46 grams per liter wash obtaining, working with a bismuth catalyst loading and a current density of 1.5 milligram per square centimeter and a current density of 200 milliampere per square centimeter. But this concentration could be obtained at the expenses of worsening the other figures of merit, that is the Faraday efficiency, the former rate, and the energy consumption. And as has mentioned before, more details of this study can be found in detail in the IC Journal manuscript published on 2020, entitled Gas Liquid Solid Reaction System for Carbon Dioxide Electroreduction to Formate without using supporting electrolyte. Finally, I would like to acknowledge to the organizing committee of this International Conference on Chemical Reactors, to the financial support receiving from the Spanish State Research Agency, through the different projects, and finally to the University of Cantabria for the registration of this International Conference on Chemical Reactors. Finally, I would like to thank all the audience, and thank you very much for your attention.
Yeah, many thanks for your presentation. Thank you very much. So the talk is now open for discussion. Maybe there are questions from the audience. Maybe I start with a warm-up question. Actually, I have two questions. One is there some quality for the CO2 needed? I mean, typically we will catch the CO2 from either some combustion processes or from air. So depending on how we do that, there might be some impurities. So is that a problem? The first question. And then the second question, I'm not sure whether I missed that, but do you get other products than the formic acid? So is there some selectivity issues?
Well, I start answer your second question. We analyze, it is true that in this presentation we only focus on the formate as a liquid product obtained in the output stream of the electrochemical reactor, but in the manuscript that I have mentioned, all the phases were analyzed, and well, answer your question, as a liquid product only formate was detected, but in the gas phases we obtain hydrogen, carbon monoxide, and in some cases, and in some, depending on the operating conditions, we can obtain also ethylene. But in general, the main products that close the mass balance are the formate in the liquid phase and the hydrogen and carbon monoxide in the gaseous phase.
Okay.
Can you repeat the first question?
That was about the purity of the CO2. Whether
Okay, well, in this step, we study the influence in this case is of the configuration of the electrode and the electrocatalyst, that is the bismuth carbon supported nanoparticles, and the purity of carbon dioxide that we use is purity of 100%. But it is true that for a future implementation of the process and industrial scale, it is necessary to study other purities in order to close this process to the real life, that is the real purities that come from the industry. But at this moment, we study the purity is 100%. It's pure carbon dioxide.
okay. Are there other questions? Then maybe I ask a last one. So speaking about this CO, can you give us a rough indication how much of the carbon ends up in the formic acid or the formate, and how much goes to the CO? So kind of a carbon efficiency, that we understand where the CO2 goes.
To carbon monoxide, did you say?
Yeah. So how much of the carbon goes where? That is in principle my question.
In general, the main product is the formate, and in the gaseous phase, the hydrogen, the concentration of hydrogen is higher than the concentration of carbon monoxide, because with the use of bismuth, one of the objectives is that hiding the concentration of hydrogens with respect to other products. But in general, the main products are the formate and the hydrogen. For example, when I explained that the Faraday efficiency for formate is approximately 50%, maybe the Faraday efficiency for hydrogen is maybe the 35%, and the other 15% is carbon monoxide, more or less. The carbon monoxide, more or less, is approximately 10%.
Okay, thank you very much. Okay, so that would be the last option to ask a question to Dr. Diaz-Sainz. So it seems to be all very clear. Thank you very much, Dr. Diaz-Sainz, for your presentation once more. And now we proceed with the sixth presentation in that session. And it's my great pleasure to introduce Pier Domenico Biasi from Casale in Lugano in Switzerland. And we now will hear a presentation on the way to validate a new ammonia synthesis catalyst. So that is something which came up in a collaboration between Casale and Clariant. So we are really interested in your talk, and the floor is yours, Pier Domenico.
Okay, thank you very much, Tilma, for the nice introduction. Today I will speak how to validate a new ammonia synthesis catalyst, and this is a collaboration between Casale and Clariant in the way of the ammonia synthesis and the green ammonia. So Casale is a technology and engineering company that was founded in 1921, and this year is the centenary of our company. And the first technology that was developed by Luigi Casale was the ammonia synthesis. Why he developed the ammonia synthesis? Because Haber and Bosch discovered how to make the synthetic ammonia, but they were not licensing the process to other partners. So Luigi came up with a new process and at a high pressure that could be licensed to other people. So keeping this in mind, he sold the first technology in Japan. This is very important to understand how our company is always keen to new technologies and to new way of discovery. So in the 80s, we developed urea and methanol technologies, and in 13 and 14, we acquired from Borealis 2 technology. We are 400 people, mostly based in Lugano, and then we have a sister company that is more on the engineering side in Prague, in Czech Republic. But what is important about the Haber-Bosch process? That to arrive to the ammonia loop, you have to treat the gases, you have to purify them to transform methane or the coal gasification into syngas and hydrogen, and then you have to remove also the CO2 to arrive finally to the ammonia loop, where there is the catalyst of the ammonia synthesis. And for this reason, this is an iron catalyst that was developed around 100 years ago, but was modified during the years. And what was modified also with the technology of the reactor. What is important is that the catalysts suffer of poisoning of oxygenates. So you have to protect the reactor like a baby and to arrive with a few ppm of oxygen and other poisoning to the main reactor, to the syn loop. So the catalyst for ammonia synthesis is based on iron oxide precursors. At the beginning of the century, most of the catalyst was based on magnetite, wustite precursor, and as a catalyst, because it was oxide, then you needed to reduce inside the reactor. But then in the latest 90s, there was a discovery from Professor Liu from China that was discovering that the iron oxide in form of wustite was the most active compared to magnetite base oxide catalyst, because also the structure of the catalyst and the promoters that were added to the catalyst and they were interacting with the iron were more effective compared to the magnetite base. And as you can see, Clariant acquired the Wustite base catalyst, the Ammomax 10, in 2002. So as you can see on the right hand side, the Wustite based catalyst is always better performing compared to the magnetite catalyst. This is because Clariant has some also proprietary precursors, some proprietary also promoters that are added to the catalyst. So most important is also the catalyst activation, because a proper reduction of the catalyst make the catalyst more or less active compared to what is expected. So it is important to know that based on this condition, with the Ammomax 10 catalyst, with a Wustite based catalyst, you can improve the production of ammonia, but also you can have less water evolved in the Ammomax during the reduction that makes the catalyst more robust, because water is a poisoning, and also the faster reduction make the catalyst more convenient for the plant operation, because the shutdown is limited. So based on that, we started to discuss with the Clariant to develop a new catalyst, to have as a target a new catalyst that could be also tailor-made for some engineering and some new development also of reactors together with us. So we identified some targets, we work with them, and then we obtain some new possible catalysts. And I cannot disclose the new catalyst, what it is, but I can show you how we interacted together and how we developed and how we arrived in the implementation of the new catalyst. So first of all, to test the catalyst and to compare the catalyst, we got a lot of formulation from Clariant, and we started to test them in a tubular reactor at high pressure, representative of the industrial condition, at a different temperature to study the kinetics, but also with the inert dilution of methane in the gas stream, because this is really important in the feed stream, also when you calculate the kinetics and also when you have the operation condition with the catalyst. And what we observed that we found a formulation that was outperforming the classical Wustite and magnetite formulation, that was really performing well at high temperatures, especially when we are limited also by kinetics and thermodynamics. So the new formulation was outperforming, and also increased a gap to magnetite classical catalyst. But this to implement the catalyst, or you go to pilot phase then and you do, or you try to understand how to implement at lab scale some new technologies and some new type of testing to avoid the pilot plant. So first of all, as I mentioned at the beginning, the poisoning is something that is really important for the ammonia synthesis catalyst. So we did some preliminary work understanding what was the effect of poisoning of oxygen, of water, of carbon monoxide and carbon dioxide, and they were pretty similar. So we decided to work with the oxygen, and with oxygen at a low concentration. As you can see, we did some, these are reporting of some tests, but we did also between 0 and 6 ppm and between 6 and 16 ppm. There are three main steps of 0, 6, and 16 ppm. 6 ppm of oxygen is the limit that usually the catalyst producer says to the plant managers to operate the plant with the maximum amount of oxygen. So we tested the catalyst with this kind of amount of atomic oxygen in a broad range of temperature to see the effect where was limiting, where the problems. And as you can see also during the catalyst activation, when the catalyst is active, especially with the 6 ppm, you have here a problem, but because you cannot make the proper light off of the catalyst. So we saw, but already here, that the new ammonia casale was more performing, especially also here when 10 degrees of temperature make a big importance in the economic of the plant. So, but since the ammonia synthesis catalyst last for more than 15 years, we needed also to find an aging procedure that was representative of the aging in the real plant. So what we did, it was that we were working with the Clarion, understanding the type of the performances of the plants. We established a procedure for a faster deactivation, and we did several cycles that are representative of several months of operation in the real plants to understand how faster was the deactivation compared to Wust-type catalyst and to magnetite catalyst. And we saw that the new ammonia casale was more performing and more stable compared to classical catalyst that we had, because also here you can see that the slope is lower here compared to the classical Wust-type. But when you implement a catalyst in new catalyst with a new formulation in the reactor, you need also to understand the mechanical features of the catalyst. So we develop a tester in the lab for the interaction between the catalyst particles and the walls of the reactor, because when you have shutdown, startup, when you load the catalyst inside the reactor, you have this interaction that are really important, not to break the catalyst. Then there are also pressure drop tests that in this case we didn't perform, but is also right to mention, because you can do experimentally with the you can do with the simulation, but also a confirmation with the experimental is really important. And also we tested the shear stress, that is the unit to make the stress between catalyst and catalyst particle that they interact together, and how much is the shear stress. So given this, given the positive results, we passed to the simulation, to the process simulation that were done in our process department. So we determine the optimal reactor design and the condition to run the new catalyst. And we saw that also the best configuration was to use the Ammomax in the right places, and also when there are some limitation, kinetic limitation. What is important that we optimize then the reactor to make the profitable also this new catalyst. And we made a case study, and what was the result was that we could save 40,000 kilocal per metric ton of ammonia, reducing 3,500 tons per year of CO2 in one plant. And also in case of the plant capacity was limited by Saint loop, to use the ammonia casale was leading to 10-15% of increase of ammonia. So we had the opportunity at the beginning of 2020 to install the catalyst in a revamping of a KBR converter. We placed the Ammomax casale also for safe side risk mitigation only in the third bed, and we made this case for the client accepted, and then we loaded the reactor in 2020. So what we observe is that we make the new reactor and the catalyst, we make the revamping, and we compare the performances before and after the revamping. What was really important that we were able to reduce before and after the revamping by almost 20 bar the inlet pressure of the Saint loop, and also to increase the outlet of the ammonia by 2% relative that went from 12 to 14. These results were also exceeding the expectation, and client was really happy and still happy because the catalyst is running since almost 2 years, and we were made the first reference, and we were able to sell the catalyst and the new revamping with the client in an efficient way. So to summarize what we were able to do, that the idea to market was in less than 4 years because we were communicating and we had a good relationship with the client. We adapted the new reactor to the catalyst to make the performances at the best, and we had also the first commercial reference, and then in few months also new reference will come. We have seen that the catalyst has a higher tolerance toward poisoning and aging. The higher activity was very good and was really appreciated by the clients. And then at the end of the day, we needed to make the client satisfied. So they were really happy, and we also were able to show that we want also to go to green technologies, to green ammonia, and to lower the environmental impact of this technology. So this was a successful collaboration. I thank Casale and the client for the opportunity to develop this program on the AMMOMAX. And lastly, I wanted to share with you that we are, since it's our 100th year, we are organizing some mini symposia. You can check the Swiss Chemical Society web page, and will come. The next one will be in catalysis in November, and then also in modeling for engineering, molecular modeling for new catalysts and new materials. I thank you, all of you, and I give back the word to Tilman.
Yeah, thank you very much, Pier Domenico, for this very fascinating story, and congratulations for this success. It's very nice if something which starts in a lab really ends up in a real plant. So we don't see that often, but quite happy to see it. Yeah, the talk is open for discussion. So maybe a little bit to warm up the audience. My question was the aging test you did. What is it? Is it only doing some pressure and temperature cycles, or does it also contain some impurities? Or can you tell a little bit? Because I saw a number of cycles, but most probably you have a phase where you stress the catalyst and then you have a reference test, most probably. Yeah.
Exactly. The reference test is done in classical condition. I can go back in the presentation. So this is the reference test done with the normal reaction condition, so pure hydrogen and pure nitrogen, and then between a test we were doing cycles. I cannot give the precise because it's confidential, but we were using poisoning, we were using stress of temperature, stress of pressure, and also stress with the poison. So it was a mixture that was representative of the industrial cases, because also during the industrial you have unexpected event, water leaching, other type of poison that can enter, and so you needed to be as much as representative. We made a lot of tests to achieve something that was pretty reliable, and then we did. And so we took into consideration all the parameters that you can find in the plant.
Okay, thank you very much. Are there other questions? Yeah, that seems not to be the case. I think maybe at least the people in Europe are already looking for lunch. In that respect, I would like to thank you, Pier Domenico, for a really interesting presentation, and actually all speakers of that session. That was really a fantastic travel through many different aspects. So thank you very much, all of you, and also the audience for staying with us, and I wish you a nice day. We now have a coffee break and we reconvene at in 20 minutes, so 20 past 12. So thank you very much.
Thank you, Mr. Chairman.